Hello, good afternoon. My name is Barbara. My name is Nayani. We are going to present Minerva Rockets rendition of the EVA spacesuit. Minerva Rockets is a team of UFRJ in Rio de Janeiro, Brazil, and our spacesuit is named MR1. Our presentation plan includes an introduction, our research methodology, the suit overview, its specifications, and a conclusion. An EVA, or extravehicular activity, is any activity performed outside of a spaceship. So it can be on the vacuum of space, or on a planet, or on the moon. In this image, you can see the first ever woman who performed an EVA. It was a Russian in 1984. Our group chose some EVAs which we thought were important, starting with the first ever EVA, which lasted for only 12 minutes, and until 2001, which there was an EVA which lasted almost 9 hours. So we can see this evolution of the spacesuit that allowed this bigger time to be possible. Here we can see a timeline of spacesuits, and we can see the developments that were made in each and every one of them. Our research methodology included a literature analysis where it took articles and books about the environment in which the EVAs were performed, and about the specific components of an EVA. We designed our spacesuit using HB pencils, fine liner pen, and the program Illustrator, and we used the Z2 spacesuit from NASA as a reference, as a general reference for our project. This is our spacesuit design. It was loosely inspired by the Ghostbusters because they are explorers and they face new things just like astronauts would. But we had to do lighter colors so as to keep the spacesuit safe from radiation. So there are those reflective coatings like the silver and the red ones to make the spacesuit reflective. Basically, our spacesuit weighs about 25 kilograms, the main spacesuit, and it has an operating pressure of 4.8 psids and a maximum operating pressure of 13.2 psids. And these pressure are relative to the environment. So if the suit is on a higher pressure environment, it can reach higher pressures, inside pressures, such as 1 atm if it's necessary. So the suit is composed by soft materials, which are the fabrics, and hard materials, which I will explain later. The soft suit materials are arranged in layers. The first layers, the one that is closest to the skin, is the liquid cooling and ventilation garment, or LCVG. It looks something like this, figure 6B, and it is made of nylon and spandex. It's a bodysuit and has these plastic tubes through which flow water. And the water is cooled by the backpack, so when it flows through the body and close to the skin, it takes away the heat produced by the body. And this is necessary because the suit is almost completely thermally insulated. So there's almost no heat exchange with the environment. This means cooling the skin off is necessary to maintain livable temperatures inside the spacesuit. This image is just an example because our LCVG has a hood, and through the hood there goes another tube, a tube loop that goes from the head to the hands. And this is because the head is the one that produces the most heat and is at the most risk of overheating. So, and the hands are at the most risk of freezing over. So it takes the heat from the head and to the hands. And then over the LCVG, there is the pressure garment, which is made out of Dacron and nylon. And it serves as a way to contain the pressure, and it allows the suit to be inflated. and it keeps the atmosphere inside of it livable. And the pressure inside of it, the ones that I told you before, the 4.1, about 4.1 psid. Over the pressure garment comes the thermal micrometeoroid garment, or TMG for short, and it has a double function of thermally insulating the suit and protects it from damage. So the thermal insulation traditionally was made using a multi-layer fashion of mylar and dacron. So there will be about 7 layers of each, and this works very well on the vacuum of space or in places where the atmosphere, where there's low atmosphere, like the moon. But it would not work on a place with gas atmosphere like Mars, because there will be gas convection, air convection between the layers, which would render the insulation almost useless. So we had to find some layers, some thermal insulations that were only one layer or few layers. And we actually use Primaloft, which is not only a thermal insulation, but also waterproof. And it has these voids inside it, but these voids aren't connected, so there's no air convection. So we call it they're contained voids. And to make it even more insulating, you could use these shapes of fibers on the Primaloft layer. They're called 4DG fibers, and they allow for more surface area, so it insulates the suit better. And this image 6A is a cross section of a fiber with this shape. And you could also use silicone air gel to fill those voids. And air gel is something that's very lightweight, but it also has these voids which are not connected, and so it would further better the insulation. And the micrometeoroid part of the garment is the protection part. So it protects the spacesuit from puncture, tearing, abrasion, and especially damage from micrometeoroids, right? Impact with these micrometeoroids, which are these tiny particles, well, they can be tiny particles, that just zoom around in space at really high speeds and can actually damage your spacesuit a lot. So this protection from abrasion is made from Kevlar and Nomex. And these 3 layers that I told you about, the TMG, the LCVG, and the pressure garment, go under the hard parts of the suit, the hard components of the suit. And now the dust cover, which is also made out of fabric, goes over everything. Because the dust cover is one of the most important parts when you're going on a planetary activity, because they protect the suit against regolith. Regolith is this really fine dust that is found on the surface of planets like Mars or on the moon, and it just clings to the suit in a way that's really hard to take off, and it can contaminate the vehicle or the ship if you go back to the ship without taking it off. And it can cling to the visor, so you can't see anymore through this dust. So there's this dust cover that's made out of Vectron, and it has a coating of silicone. And on the dust cover, it's also possible to have active protection or passive protection. Active protection has this name because it uses a low current, electrical current, and it makes this electrodynamic dust shield, which is a weak electrical shield that is uneven, and it travels through the spacesuit, and it basically doesn't let the dust cling. It doesn't let the dust find some place where it can stay on. So it's first of all, the dust doesn't cling as much, but also it's easier to take off. And the passive protection we found is a work function matching coating. And what does it mean? What does work function mean? Work function is the energy necessary to take one electron from some material. So if you take one electron from a material, it gets attracted to other materials, right? So if the work function of your spacesuit matches the work function of the dust, then the dust isn't attracted to the suit anymore. And it's way easier to take off the dust, even if there is some regolith on your spacesuit, it's way easier to take off on an air shower, or if you stomp on a grated porch, the dust just falls off easier. And the gloves are a very sensible part of the suit because they have to allow for high mobility while also keeping a really good thermal insulation, because the hands tend to be the coldest part of the body. And it basically follows the same principle as the rest of the soft suit. It has a restraint, which is fitted to the hand. Here in figure 7, you can see that. There's a restraint. Over the restraint, there's a pressure bladder. And over that is a TMG, similar to the one on the main suit. And on the palm of the glove, there is this, they call it a vulcanized rubber, which not only helps the thermal insulation, but it also helps grip. So it can hold things easily with this rubber. And in the back of the fingers, you can also have aerogel pads to better the thermal insulation. And one thing that's interesting about this glove is that we took a reference from Phase 6 and Phase 7D NASA gloves, and they made some tests with these, some sensibility tests. And with these gloves, a subject could actually feel gaps that were narrower than 0.2 inches, which is about half a centimeter. And this means that you can feel the difference between keys on a keyboard, because the gap between keys is usually more than 0.5 centimeters. So you can type away in a keyboard even with these thick gloves. And what it also means is that these gloves are touchscreen compatible. If the touchscreen uses pressure, right, is a resistive touchscreen, they work just the same. You press on a place and you press the button. If the touchscreen, however, is conductible, you would have to sew a thread, a conductive thread, like a silver thread, that connects the skin of your finger to the tip of the fingers of the glove. So then it would work just as well. And the boots, there are two types of boots for two different EVAs. So in an activity in our space, if you're just hanging from the spaceship and you're making some maintenance or something, and there's no gravity, you wouldn't need a full hard-soled boot. You could use a soft boot with this aluminum heel. This heel connects to the spaceship, so you don't float away and you can use your hands. For planetary exploration, however, you would have to use a boot with a hard sole and with more structure, especially on the ankles, to avoid injury. And we chose this La Sportiva's G2SM boot because it's a mountain climbing boot, which means the thermal insulation is one of the better there is on marketable boots. And it also has this BOA closing system that you can use. You can adjust the boot even when you're wearing thick gloves. Like on this image, there's an astronaut adjusting both boots with this closure system at the same time. So it's way safer for the astronaut, and it has a better thermal insulation. Now there goes the hard components of the spacesuit. So the hard upper torso, the HUT, goes on the torso, right? And it's basically an external pressure chamber. So it keeps the pressure and it keeps the shape of the suit. And it's another safety layer for the suit to keep its internal atmosphere. And it gives the astronaut structure. So the weight of the suit is distributed through this hard component. And it is made out of graphite carbon fiber, which means the HUT is really lightweight compared to other kinds of HUTs. The HUT has these 4 rings. There's the helmet ring. There's a helmet ring, and there are 2 shoulder rings, which are called size bearings, and there's a waist ring down in the below, right? And behind the HUT, there's an opening, and through this opening, you can get inside the suit, in a way that's way easier than if you just put every layer on. And you can see here the subject entering the suit from behind, and in this really easier and faster way. She's also wearing, you can see, she's also wearing some layers of the clothing, and some layers are attached to the hut. The layers she's wearing, if she's going on an EVA, she would already be wearing LCVG layer and the pressure garment, and the TMG would already be connected to the hut, making it easier to put on and take off. And what this rear entry, what this back entry also allows is that you can keep the spacesuit outside of your vehicle at all times, like on figure 14, and you can get in the suit from inside the vehicle and you would already be outside, which would minimize the chances of regolith contamination of your spaceship. And this, now you can see a video of the woman entering the suit from behind and then adjusting it afterwards. You can see it's very quick, and you can basically do it easier. So another interesting thing of the hut is that it's adjustable. So when you go out in space, your body changes a lot. So there are this cycle that first your limbs swallow and then you go back to normal. So if the suit was really fitted, you'd have to have several types of suits, several kinds of suits for each crew member, and several suits for every different type of body. And because this suit is adjustable, you can actually use the same suit for everyone, basically, or most people. So it's way less things you have to carry, and way less weight, and it's easier to mass produce if necessary. And these are the connections and materials. There is the shoulders. We can see these layers of the shoulders, so we can move better. The waist joint, which rotates, and the brief shell, which goes under the waist joint. And the helmet that goes directly on the hut. It's necessary to have a visor which is clear so you can see, but it also has to be reflective, so the radiation don't, first of all, blind the astronaut or damage him in any way, because radiation can damage if there's not as much atmosphere. So there's this gilded visor, like in figure 21, that you can rotate down, so there's this reflective barrier. And here you can see the man just putting it down, like so. On the helmets, there are cameras and lights, so the astronaut can see better, and so the base can collect that data. And the astronaut also uses a cap with headphones and microphones, and with a headphone and a microphone to communicate with the base. And here are some examples of mobility: the moving of the arms and the shoulders. Here you can see a spacesuit on a rover. Like I told you, you can get from a vehicle inside the suit, and someone walking normally with a suit, even on the sun, under the sun. And here you can see them using a tool. You can see them bended down, so that proves the joint is really good. And you can use a tool which proves both mobility and the grippage on the glove.
So now we're going to talk about the primary life support systems, PLSS for short term. We were able to study all basic functions like air oxygenation, removal of monoxide of dioxide, power source, which is very important if the activity is going to last for several hours. We studied refrigeration, communication, and warning systems. Here on this image, we can see all the integrating parts in this backpack. We can see the tanks, the air circulating system, and the power source. Here is our drawing showing how we're going to use this space in the backpack. We have the oxygen tanks, which have 25 liters each one of them. We have a refrigerator peristaltic pump. We have a communication systems, a rebreather, and a racing battery. So for the refrigerating systems, we think about the principle of refrigerating water using vacuum space, because there is very low temperatures. So we use water that goes circling in these microtubes here, which you can see on this image. And this pump is used to circulate this water so we keep in movement in the body of the astronaut in the spacesuit. For atmospheric recycling systems, we use this system that is very similar to a diving suit. So we have the oxygen tanks and a diluent tank, and we have a valves that is open only in the case of the oxygen. When the levels of oxygen are very low, this valve is open because of the sensors that can sense the levels of oxygen. And we have, when the levels of oxygen are very high, we have another valve that opens the diluent tank. We also have a canister, which allows the purification of the air, so the air keeps always circulating in this canister here, which gets the purified air as an output. For control model, we have this multi-mission platform, which was developed by our team. It can work in different missions like CubeSat that we already presented today, and also in rockets. It is a microcontroller which has processing power for reading different kind of sensors. It can send data and receive data. Can receive data from sensors in the body of the astronaut and external data from the environment, and it can send data to the base and to the astronaut. So for biomedical equipment, we can have the measure of the heart rate through an electrocardiogram, which is also known for ECG. It is very validated in the clinic, so we're going to use something that is already been used for years from now on. And we will use these systems which have two electrodes, like this image A here, and it's a system already used for by NASA, for example. We have also measures of respiratory rate, which we can treat this data that come from the ECG and get then the respiratory rate. For oximeter and blood saturation, we are going to use this oximeter on the wrist of the astronaut. Here you can see on image B. And for blood pressure, we are going to use a wrist device also on the other wrist of the astronaut. For temperature, we are going to use this thermistor that is a resistor that changes its resistance based on variations in temperature. It's very sensitive, so we can collect the minimal differences in temperature, which is very important for our work. Okay. For dehydration signs, we are going to have to monitor the water metabolism of this astronaut. We are going to do this by sensing how much water he is ingesting and how much water he is losing by sweat and by urine, if it happens. And we have also an electroencephalogram, which we will also use electrodes, but then in the head of the astronaut. Depending of the position of these electrodes, you can have different data coming through these electrodes. So if we position these electrodes in the limbic systems, we can have emotional and thoughts that we can have this electrical impulse coming from, and we can read it. And we have also positioning these electrodes in the motor regions of the brain. Here you can see in A the result of all this analysis. For stress detection, we are going to use a very large number of systems like electrocardiogram, electromyogram, galvanic response, and breathing. And analyzing all these results, we can get some kind of idea if he's going through some stress or not. And for disease detection, which was an innovation in our work, we are going to detect these volatile organic compounds through breath. And depending on what compounds is found in this breath, we can know if he's having some kind of abnormality going through the body of the astronaut. So for space radiation, we are going to use this Geiger-Müller detector, which you can see here on A. And he's able to detect ionization particles, and he's going to be positioning in the waist of the astronaut. He's also going to be a detector inside of the spacesuit. So for conclusions, we were able to make a lightweight, compact, and low energy EVA. All minimum requirements were fulfilled. We have a maximum height, umbilical cord, communication systems, and we make a spacesuit able to function in microgravity and in Mars environments.
And for functioning on microgravity or Mars environments, you'd have to make minimal changes like the boots or changing the oxygen tanks for an umbilical cord or changing the refrigerator, but they are minimal, so the same suit could be used for either of these activities.
Yes.
That's it. If you have any questions, anything you want to say, you can ask now.
Team, congratulations for the amazing project. It was a very complete work, very complete project, very complete study. You are to be congratulated. I have a few questions I would like to ask. So first of all, one of the main challenges on Mars manned missions and human colonization is dealing with Mars dust and radiation. What would be the effect of Mars dust and radiation in your spacesuit design and operation?
So, like we said when I was explaining the dust cover, you could use several different approaches to this. First, I'll talk about dealing with the dust. So, our dust cover is already coated in silicone, which makes it easier to take off the dust and makes it harder for the dust to even cling to it. But you could also use these passive or active shields. The active shield is the one with the electrical field that travels through the suit, and it dislodges the dust from the suit. So that will be one thing. The second is the passive one with the work function matching coating, and it changes the chemistry, basically changes the chemistry of the situation, and it doesn't let the dust settle. If there was a Mars habitation and you would do an activity outside of the station, you could have a suit that's always outside, like we showed. You come from inside the vehicle, or in the case inside the house habitation, directly to the suit, so there's no contact from the suit to the living areas. But you could also have this the systems like an air shower that would blow off the dust when the astronaut will come back, or these grated porches in front of the entrance, and where the astronaut would stomp off the dust. So especially these things would be necessary with the shields. So the shields make it harder for the dust to cling, and then you stomp it off or blow it off, and then you have basically a clean suit, and that doesn't suffer from the dust out there. From the radiation, first of all, we made the whole suit white or silver, or use reflective colors, like the neon red on our suit. So the radiation usually just reflects off. In the visor, there is that gilded visor with the reflective coating, which can sometimes be gold, if I'm not mistaken. But that basically wears the radiation off. And with all those layers, it's harder for the radiation to even get to the astronaut. So they would be fairly safe from it, especially with the time of EVAs that are being used today, that not more than, I think, 20 hours. They wouldn't be in contact with these things for that long.
Thank you very much.
Welcome.
Hello, can you hear me?
Yes.
Yes.
Yeah, it's Eduardo Alho.
Hi.
I would like to first to congratulate you for the presentation. It's very nice, as was the work. And first, general question: if you would summarize, what would you say are the main differences from your suit from the Z2 from NASA?
Okay. First of all, I would say the part I researched the most, at least, was the thermal insulation. They, for what we could find of the work they published, they would still use the multi-layered fabric, but as we said, that wouldn't work very well. So the Primaloft is an innovation. The radiation controller, I think, would be two. And the
biomedicals equipment, there is a lot of that thing that is innovation for articles and everything that's being released this year. So it would be an innovation, not so for them, but also for us. And then I think it could be some innovation.
And we also simplified the PLSS to fit in the
control model.
Yeah, the control model, the PMM. The PMM is a thing that our team kind of developed, so Z2 wouldn't use something like this to our knowledge.
I think the integration of everything that we did, it's an innovation. It's not Z2 at all.
Yeah.
Okay. I would like to go to also a little bit of the biomedical sensing.
Okay.
And the first question, so the ECG, the electrocardiogram, you use two electrodes, and and also use two leads for the D2 and V5. That's right, as I read on the
I use an article from NASA that he had this system already integrated and functional. So I only use the sensors that they cited on the article. Yes, but I think when the dois use.
Have you seen something about giving a feedback loop? Like, do you know this defibrillators, automatic defibrillators? They work also with two leads, two electrodes that can collect data from electrocardiogram, and they can sense. They have an algorithm that can sense, for instance, a heart attack or a stop on the heart, and then can deliver electricity back to the astronaut, for instance, to reanimate if that there is a case.
Oh, that's amazing. No, I haven't read anything like that. I'm sorry.
I don't. No, I don't think that has been integrated into some suit or something. But perhaps this is an idea that you could go for, and could be something that would be interesting to integrate, not just in the electrocardiogram, but how would this signs that you are getting could you have to have a response from them? For instance,
because then you will only watch him die. Like, okay, now he's dying, and that's it.
For the stress.
All the sensors. I mean, they have to be integrated, and then you have to have a feedback on that. Something also that I would say that the pressure, the measurement of arterial pressure, these sensors, wrist sensors, are really not a good idea, I guess, because the accuracy is very low and they decalibrate very easily.
Oh, okay.
And they have a kind of a huge volume, and perhaps this squeezing your wrist in activity that could be not very, very, very nice. And also the oximetry pulse, I don't guess that this commercial oximetry pulses are the best. There are some from the anesthesiologists are very tiny that you put just on the fingertip or in the earlobe, and then you can get very hard. Yeah.
Usually,
I think that one of the most challenging in the biomedical equipment was measuring pressure, because the only equipment that I was finding was the one that we usually use on clinical. That is the enormous equipment, and I don't think that would be usable in our work. So I look for the smallest one. And for blood pressure, it's very difficult to measure with miniaturization, and we can say that.
But also, all the things we took directly from the market, we weren't. If we were to take this forward, we would get, we would send them projects. So we would base our project on something that's already existing, but we would send the sellers specifications for what we need and for what we want. And these with the biomedical equipment, or even the boots, the refrigerator, they are sold in markets, but we would always send them our project and our needs, because that's a very specific thing to use them for. So it wouldn't be just off the shelf.
Yeah,
it would be something we would ask them to do.
Yeah, and we think about doing a reverse engineer. I don't know if I can say that, but it's not going to be exactly that equipment that we're going to use, but we will open it up, use the sensor that the equipment has, and then integrate it in the way that we want. Like, that was my idea, actually.
Of how things are developed for space ships, and then we use it afterwards. So we customize things, and then perhaps they are useful. But in the sense of the pressure, there are some algorithms that you can infer arterial pressure from the other data that you already have, like pulse oximetry and electrocardiogram. And perhaps just finding how to extract that information from your sign could be also an interesting solution for that. So you don't need to put a wrist measurement, so less weight, and just getting through the things that you already have. What else? Just the last thing. So the idea of the disease detection, I thought was very nice, very good idea, and I would like to see this in an experimental setting. Would be very nice. And the last thing about the electroencephalogram, very nice things can be done with that. I don't know if you have seen that brain-machine interfaces that you could catch, could control, for instance, drones or tools, or even rovers, just with the sign that you get from the EEG. I think that could and should be explored in the future. But then what you said, like you can get from limbic parts of the brain and detect signals of stress. Perhaps this is not so straightforward. So it's difficult. There are algorithms to clean up and to detect that. They are not so easy. And you have to have a pre-processing. I think getting that live, online, I mean, wouldn't be so easy. But yes, I think that you should go deep on that. You can have many other applications from getting the EEG data. Have you?
I can only say one thing about this electroencephalogram. It was developed by a friend of ours of another university. I think he is in the paper that we send, and he already has some MVP. How we say that in English? Minimal viable product. He developed. He developed here on Rio de Janeiro. I think 2 years ago, and he only presented to us his idea, and then we thought, oh, okay, this works perfectly for us, and then we implemented it in our work for our needs. And I think that because he already
in detecting epileptic crisis before they happen. So you can analyze the signal and you can decode the signal. And then there is a guy who had done this. I think they are here in São Paulo. And you can predict a epileptic seizure like 25 minutes before it happens.
Yeah.
With processing of the signal and so on. So, and that a suit should be able not just to warn, but to take actions on that. I mean, if you're outside on the space and you know that you're going to have a seizure, so you have to have a warning to come back or something, stop doing what you are doing. And actually, the main idea of biomedical sensors are how can you give a feedback to the suit about the signals that you are getting from them. So I think that's it that I had to ask. Congratulations once again, and I hope to see that suit someday in the future.
Me too. Me too. Okay, more questions?
Anything else?
Yes, I have another question. We're asking this for every team in the COBRUF Aerospace competitions. What was the most difficult topic you faced during the project?
The literature,
the research, because there are a lot of works, but they're usually very general. They're not detailed. So you would find a work that claimed to explain how to make a suit and every component, but then they would go and say something like, "Oh, it's plastic. Oh, it's soft materials," and you wouldn't know what the actual materials were. You wouldn't know the thickness of the layers, and none of it was detailed. So you would go one reference after another, and then you get in a work in another language you couldn't understand, and there was nothing very specific. Yeah. So we ended up following a trail of crumbs that led nowhere several times during the research.
Yeah. For biomedics, there is a lot of challenging all through the work, but to think how can I use this technology in what I need? Like it works perfectly here in this article, amazing, but how can I extract that to my my need to make a spacesuit? Like this adaptation of the technology was also a challenge for us.
Thank you.
Welcome.
Well, congratulations to the team. It was a really complete work. It has really great analysis. Congratulations, it was really, really good. Before we finish, I'd like to know if you want to say some words, a few words.
Oh, we would like to thank our whole team here, because our EVA team, just us and Vanessa and Igor and everybody else that helped us. We would like to thank Minerva Rockets as a whole and every single one of the professors that helped us along the way. And we'd like to thank COBRUF for this opportunity to develop these suits. It was really interesting. We found out things we never thought about. We thought about things we would never considered, so it was a really great opportunity.
Follow us on Facebook page, Minerva Rockets, you can search there, and in Instagram, and follow our work.
And if you have any questions, or if you want to start a discussion or help us move forward this project, you can send us an email at minervarockets@poly.ufrj.br.
Yeah, we need people interested in our work, so come, guys.
Yeah,
we need you. That's it. Thanks.